Okay, good evening. Welcome everyone. It's a great pleasure and honor to have with us our distinguished speaker, Professor John Martinez, who is this year's Nobel Prize laureate in physics. Uh, I was asked to keep this brief. So Professor Martinez is internationally known for his pioneering work on superconducting qubits. Um, and the foundations of modern quantum processes. He earned his degrees at UC Berkeley, and he has held research positions at CEA in France, NIST, and the University of California, Santa Barbara. In 2014, he joined the Google Quantum AI Lab, contributing to the first demonstration of quantum supremacy. He later worked with Silicon Quantum Computing in Australia and co-founded Qualab, focusing on improving coherence in superconducting qubits for scalable fault-tolerant quantum computing. So without further ado, please join me in welcoming Professor Martinez.
So thank you for coming out today. I really appreciate the opportunity. I was invited to Abu Dhabi for the CyberQ conference, and that was before the October event, which changed my life, I suppose. And I'm really happy kind of to change what I was going to talk about what was in the end my thesis experiment, which is what was cited for the Nobel Prize. So it's really fun to go back to that and explain it to you, and especially in a kind of a university setting. I'm really hoping people will raise their hand and ask questions because I like the back and forth, and I always learn from the questions you ask. So it's okay to do it at the end if you want, but if you want to do it during the talk, there's something pressing you want to understand, please raise your hand, and it's okay if I slow down a little bit, but my talk is not super long. So what we were trying to answer the question for my thesis in Berkeley 40 years ago was, do macroscopic variables obey quantum mechanics? And this experiment, we were able to answer that question, but this experiment led to the whole field of quantum devices and superconducting qubits. So I kind of talk about this early work as prehistoric qubits, because it was really before that word was invented and came widely known. So let's talk about why we were doing this experiment. When you study quantum mechanics, quantum mechanics comes basically with two postulates. Okay, the first postulate is kind of the wave postulate. Let's say you subscribing the quantum state with the Schrodinger equation and a wave equation. And then the second part has to do with measurement of that state. And the problem is physicists kind of find this two postulate kind of distasteful. They like to minimize things, so they really want it to be one postulate only. But generally, the two postulates is very powerful, explains what's going on. But kind of this discomfort in this is most popularly shown with what's called the Schrodinger cat paradox, which I'll talk about first. The Schrodinger cat paradox is invented by Schrodinger, where he has a box where he has a cat and also some radioactive atom. And then it's set up so the box is closed. And if the radioactive atom decays, it then opens up some poison and kills the cat. Okay, so you set up the experiment so that in a certain amount of time, there's a 50% chance of the decaying or not decaying. And then thinking about quantum mechanics, and you would say, okay, this wave function of the cat is psi dead plus psi alive. It's dead plus alive. Now, of course, this is very strange because it's a big object, it's alive. How can it be both dead and alive at the same time? But that's kind of what you think about when you break it up into the wave part and the observation particle part. Now, what happened is Professor Anthony Leggett, Nobel Prize winner for helium-3 physics, had the observation and the idea that perhaps you can explain this paradox by saying maybe nature is such that you can't have a macroscopic object in a dead and alive state. And the point is he was making is, if you looked in the literature at the time, there were no experiments out there showing that that's a sensible state, that macroscopic variables were not there's no evidence that this could actually happen. Now, he did look at one system, which was these Joseon junction system that I'll be talking about here, where he hypothesized that that's a system where he could actually do that experiment. In fact, in this system, it's the currents and voltages of this electrical circuit. Of course, the current and voltage of currents are represented by, billions and billions of electrons flowing in a wire. And that would be an example of a macroscopic system. So I'll be explaining that experiment that he proposed. We did that and extended a little bit. So that's the basic idea of what we're doing in the beginning. Now, I do want to point out that there's sometimes a little bit confusion about this macroscopic quantum mechanics. And that is that microscopic quantum mechanics is actually observable on the macroscopic scale. And the best example I show here is a quartz crystal, okay? And in crystals, you have the individual atoms lining up against each other, bonding in a certain way because of the way the atoms work. But that binding stacks up against each other over and over again over huge distances, centimeter distances to form a crystal. And by looking at the crystal with your bare eyes, you can kind of figure out what the atomic structure is at the microscopic scale, which of course is proven with X-ray diffraction, but you can see it. And all this is microscopic quantum mechanics being expressed, being repeated enough so that you can see it at a microscopic scale. We're talking about something different. Okay, and what we're talking about is taking some macroscopic object like a ball, and we're throwing that ball against the wall. And if that macroscopic object is a quantum mechanical object, some fraction of the time it'll actually tunnel through. Okay, this happens with particles. Now, normally that doesn't happen. The ball is too massive, the potentials are too big or whatever. But with these electrical circuits, you can actually do this kind of experiment. It's not so tiny. Basically, you're throwing it at a many gigahertz frequency, and the wall is made very skinny and not very high, so that you can see tiny. So that's the basic idea here. Any questions so far? Okay, great. So I want to explain the concept of the macroscopic variable a little bit more to make sure you understand that. So it's really nice to think about this in terms of real atoms and the crystal I talked about. If you have atoms at a high temperature, they're going to be in a gas, and all the atoms are going to be flying around in their own random direction. And if you want to describe that system, it's very difficult because you have to talk about what's the position and the velocity of all the particles in that gas. However, when you cool it down and it condenses, let's say into a crystal, as I've drawn here, then it's a very simple description of what's going on. You can just, for example, talk about where the center atom, the blue atom is, the center of mass. And once you describe that coordinate, of course, the angles and the position, whatever, but it's a small number, then from all the attractive forces of all the other atoms, you can describe that system very well. Okay, and that's kind of the example of the ball that I was talking about. Now we're talking about electrical system, and that's shown on the right. That's a little bit more complicated. At high temperatures, you have what's an electron gas, and because the Fermi statistics of the electron the electron gas is kind of populated all the way up to what's called a Fermi wave vector. And then the electrons are either occupied or unoccupied around that Fermi surface. But it's called an electron gas. It acts like that. And it's the same as in the regular gas. It's very complicated to describe. However, if you cool down, actually most metals, but you cool them down low enough temperature, they then condense into what's called a superconducting state. Okay. And this is a very unusual state where all these electrons are condensing in what's called Cooper pairs, and they all have a similar property. So in fact, what's happening is you have a Cooper pair going in this direction, it actually pairs with the Cooper pair going in exactly the opposite direction. And what's nice about that pairing is that it has a net momentum velocity of 0. And because all the pairs have the net velocity of 0, that means each pair can interact with every other pair in a quantum coherent way, in a strong way. And thus it condenses into this new state, kind of analogous to the solid here. Now, as the solid had a degree of freedom of where it was in this box, this superconductor with the Cooper pairs have an extra degree of freedom called a phase. Okay, it's just a number that describes the phase of these Cooper pairs, and the way that it condenses, all of those phases are the same. Just like here, all the positions of the atoms are at a fixed position relative to the center position. And all the Cooper pairs are the same. And then according to quantum mechanics, if you have a phase that's changing from here to here, that gradient or change in phase will give you a quantum current. And since all the Cooper pairs have the same phase, it can add up and to be a very, large current. And, for example, in, NMR, in the MRI magnets you use for health, they have, amps of current flowing into superconductors that produces the magnetic field. So this, of course, is a very strange state of matter, and it was figured out by Bardeen, Cooper, and Schrieffer, and BCS Nobel Prize. Very interesting condensed matter system. What we're interested in here is something called a Josephson junction, which are two aluminum metals separated by a very thin oxide, aluminum oxide. That's thin enough so that a Cooper pair coming across here can actually tunnel through that barrier and thus give you a current. And the current is given by this equation here called the Josephson equation, where current is equal to a materials parameter, which has to do with the size of this and the thickness of the barrier, and times the sign of the phase difference between it. And notice that the gradient of phase, the change in the phase, now just turns into a phase difference between the two, which we'll call delta. So as you see from that equation, the maximum current is when delta equals pi over 2, and then I equal I0. And then below I equal I0, this is in a supercurrent and everything's fine. When I is greater than I0, then some other things happen, and basically the superconductor turns into kind of like a regular metal. There's a voltage across it and it dissipates energy. And what we're actually looking for in the experiment here is the transition from the supercurrent phase to the voltage phase, when you get sine of delta is very close to pi over 2. Okay, so that's the basic idea of these devices. Yes. But here it's a continuous current.
Also, one individual state in quantum mechanics. What would be the analogous quantized state?
So I'll talk about that, in the next slide, what happens with further. So this has quantum mechanics in terms of condensing. Like there's quantum mechanics that condense these atoms, and it's quantum mechanics that's condensed this. But this equation here for, normally for Josephson effect and for many years, that was thought as a classical equation. There's quantum mechanics that produces this, but in terms of this macroscopic variable, that's called classical. And that's the way that you think about this normally. Okay, thank you. That was actually a very good question for me learning how to explain this better. And any other questions? Okay, so what happens is here, normally you have a current below the critical current at 0 voltage. And then when you get above the critical current, you then switch out to a voltage state, which has to do with breaking the Cooper pairs, superconductivity, but it doesn't matter. Just superconductivity doesn't work anymore. And it turns out that you can take that sine of phase physics of that and turn it into a potential, which is called a tilted washboard potential that describes what's going on. So what happens is when I is less than I0, then you have the tilted washboard potential, and point A is the phase is sitting in one of these local minimums. And it may oscillate back and forth, but the mean velocity is 0. The voltage is proportional to the velocity, so it's in the 0 voltage state. And then when you get to the critical current, you tilt that washboard enough that it escapes and it starts running down the well. And that velocity turns into a voltage, which is what we see here, A and B. Now, what we're interested in is as A very close to the critical current. And in that case, the escape from the well can be approximated very nicely by a cubic potential. Okay, so and then you turn it into a classic physics and chemistry problem of the escape of a system out of a potential well, which you probably solved already in your physics and chemistry class. You kind of know how that works. And one of the important things is if it's a cubic potential, I can describe that actually by 2 parameters. One is the potential barrier height, and then the other is kind of the oscillation frequency at the bottom, okay? And if you remember from this kind of thing, the oscillation frequency is kind of your temp frequency. And then if you, and then we go over the barrier, then you're going to escape from that. Any questions on this so far? Yeah, this is all classical physics so far. Okay, so classical physics, delta is a classical variable. Then the thermal, the thermal equation, okay, is just given by exponent of minus delta U over KT. That's a Boltzmann factor, it's an Arrhenius factor. This is the kind of thing people are familiar with, okay? However, if you get into the quantum regime, okay, then you get the escape rate is equal to some quantum tumbling formula, which is given here. So it's delta U, kind of KT is replaced by H bar omega class when there's a 7.2 factor there. Okay, and you have a different rate. And what we want to do in this experiment is we want to measure this escape rate and then see it under what conditions is a base thermal, which of course will be high temperature, or if we go to low temperature, will we see a quantum rate? And then if we see a quantum rate, it means this phase difference delta is no longer just a classical variable like it always has been thought of, but there's actually a wave function to it and it has quantum mechanical behavior to it. Okay? Questions?
In the shape of the potential, is it a dry? How can you explain this?
So what you can do is from the Josephson equations, which is sine delta, and the AC Josephson as voltage is proportional to delta dot, you can combine that into a potential problem. This is like the Josephson equation is like F equal MA. And then you can produce a potential. And what actually happens is you integrate the sign function and you get a cosine and then the current tilts down. So the tilted potential is derivable from the energy of the system. And then just when I is close to I zero, it can be approximated really well by the cubic potential. So you know that. Now, it turns out that we're going to measure what delta U and omega plasma is in the experiment. That's the important part. Unfortunately, I'm not going to go into that, but you can do that so that you can compare this directly. So in fact, one of the big things we did in the first few months working on this project was I did what I just told you. And when when you go to the cubic potential and you're now thinking about what's delta U and omega plasma, you understand really well what the physics is, as opposed to what's I and I zero and all the other parameters of the system. So this is really good to understand what is the physics. And then you can look at these equations and it's like, okay, I know exactly what to measure right now. Okay, and so that you can do the comparison properly. Okay. Now, I want to talk about two things. So this quantum formula, the fact that you have quantum tunneling, I've been trying to explain to journalists and podcasters, wave function, leaks under the potential barrier, all the quantum mechanics. That's really hard to explain, okay? And journalists just don't get that. But I can explain it this way, in that quantum mechanics is like a banker, okay? Where quantum mechanics can lend you some energy, but wants to get it back in a short time. So it only lends for a short amount of time. And the basic rule of thumb for that is to lend the delta U over some short time constant called T of traversal, so that the product of those two is this very small number, h bar 10 to the minus 34 in MKS units. So it's possible quantum mechanically to lend this to get enough energy to go over or through the potential so that you can do the tunneling. Okay, and then what's also interesting in this system is that you can have damping in the system. You normally don't think about it in regular tunneling situations. And if there's damping, that means if you're lending it energy, some of the energy is going to be damped away and lost. So you have to lend it a little bit more delta U if it's damping, which then causes this whole exponent factor to get bigger. And that's something that was actually calculated in doing these experiments to understand what was going on more deeply. And I'll come back to that later. Okay.
0.87 experimental, or is 0.87 experimental, or is it theoretically?
This 0 point?
Yeah.
So theoretically, if you want to calculate this, you do the wave function analysis and you can calculate this well. This is kind of a qualitative way to see it, but I'm going to actually show you an experiment where we measure this. Okay, which is not so obvious how to do. Okay, so I'll get to that. That's why I'm explaining it this way, because I'm trying to be forward compatible. But that's normally you do the wave function calculation if you look up in any quantum mechanics textbook. Okay, so that's the theory. So let's talk about the experiment. In the experiment, we made these junctions, and then we cooled it down to 1 to 4 Kelvin just to get some initial data to see how it worked. And the data was a disaster. It didn't make any sense at all, which is no surprising the first time you do something. And it didn't take us long to realize we were making some big mistakes here. And the biggest mistakes is that this is a microwave experiment. These oscillations I'm talking about are at like 2 to 5 gigahertz. Okay, and the way we were designing it, we weren't taking that into account. The other thing we had done is that, you're in a lab environment, you have radio frequency and maybe microwave noise in your lab that's getting into your experiment, at least noise from 4 Kelvin could be getting into your experiment. So we had to do a redesign of the whole thing to make sure that the environment and what it was engineered as a microwave device. And this represents the picture of what we built and a cross section, a diameter of that. And it's basically a good microwave engineered device here. So on the right, we have the silicon chip, which is just a T where there's a Josephson junction at the T. That's the Josephson junction. And that Josephson junction has a little bit of capacitance in it. And then it's connected to this long line here. And if anyone's familiar with microwave and RF electronics, this is more or less looks like a coax cable. Okay, so there's a well-defined wave impedance to it. And then inside of that, we actually put copper powder, which is known from NMR to damp those waves that go through there. And that acts as a filter so that if we have any noise from high temperature coming down, that all gets filtered away. And then the junction is only seeing whatever noise that would be there, at these lowest temperatures. And it's all shielded in the light. So you can see the chip down here, you can see the little cross, the Josephson junction, it's about that big. So our atom, our new atom is this wire structure that you can see with your eye. And then it goes up and there's a thermometer and there's a place where we can inject microwaves, which we'll talk about later. And then it goes to 2 more filters. And then that goes up to room temperature where we put current in and then we measure the voltage across the device. And so that's the basic experiment. And this is put in a dilution refrigerator at about 20 millikelvin, very low temperatures, because we need the quantum of energy to be h bar times, or h times the frequency. We want that to be much bigger than kT, the thermal noise. So we have to go to low temperatures, but all that can work properly. Okay, questions? Yeah. Say that again. Yeah.
In relation to ADIA, when you isolate it, there's a trajectory higher, the oscillation frequency.
Okay, so in terms of this noise affecting the junction, if it's naturally oscillating at omega plasma, if you have noise there, you're going to severely do that. And, we just made sure we filtered that there was no extra noise to doing that. In fact, what I did in the end, we had so much filtering, I put a microwave generator on the leads at room temperature and nothing happens. Okay, so that's kind of how you want to test for it. Of course, if you put microwaves injected where that connector is, that has less filtering, and then you can see that, and I'll show what happens then. So the coax cable we use at 5 gigahertz is basically a single mode. I think we only get multi-mode at 20, 30 gigahertz. And you want to shield those frequencies too, but the copper powder kind of works better the higher the frequencies. But it's only really sensitive around its oscillation frequency, as you would expect. That's where you have to be most careful. But yeah, we analyzed what happens to all frequencies and we designed it very carefully. And, we know that at high frequency, it's okay. Yes, thank you. Yeah, I'll show some data on how it works. Okay, so these are good questions. Those are the right questions. So I'm skipping the way we measure parameters and the like. I'm just getting to the final results here. So what we do is explain, we measure the escape rate And we know what delta U is. So whatever the escape rate is, we express it as KT escape. And no surprising, when you express it that way, at high temperatures, T escape is equal to T because it's more or less the same formula. And it turns out the data is slightly lower than T escape is because the pre-factor, when you do the calculations properly, is slightly less than 1. So you expect it to be a little bit lower here. And then it's T equals T escape, so everything's working fine. And then you go to lower temperatures and then it flattens out. Okay, now the obvious conclusion is flattening out because you're seeing quantum tunneling and you're getting this extra escape mechanism. But how do you know it's not noise that's doing that? Okay, so first of all, we designed the circuit so that we know that noise can't be getting into it because the filters, and we actually inject microwaves to see if that's happened. But we also can do a second thing, is that is we put a magnetic field, there's a cam that goes here, magnetic field, and that magnetic field lowers the critical current of the junction through superconductivity effects. That lowers the frequency, and then it stays classical, so you get a little bit of quantum effects at low temperature. So that's an in situ test that, you don't expect noise to be giving you this extra flattening off. And then you can, knowing all the parameters, you can calculate what the macroscopic quantum tunneling rate should be, which is quite consistent with what we measure, including all the error bars. So I'm going over this very quickly, but you can really show that things are working in the proper way. Okay? Now, the next thing we can do is look at energy levels. Now, we know from quantum mechanics of spectroscopy of atoms is that this was one of the, and seeing energy levels in the atoms is like a real strong statement. There's some very unusual physics going on, and it's kind of the smoking gun to know if you're seeing quantum effects. And what we see here, it's in small little dots. You can see that there's kind of 3 peaks going on with the data here. When I plot the enhancement of the escape rate, when we put on a little bit of microwave power. And in this particular case, that was at 2 gigahertz. And what's happening is, in this potential well, because of quantum mechanics, there's quantized energy levels. Classically, this can oscillate at the high frequency at the bottom with lower frequencies at the top, but it's a continuous oscillation frequencies when you go to bottom of the top. But when you do the quantum mechanics, you see the quantized energy levels. And when the microwave drive equals one of those transitions, you then resonantly pump energy in, and then they escape better. And what happens is at low currents down here, you have a high well with a higher frequency, and you see the 2 to 3 transition. And then as you go, the higher and higher current, delta U goes down, the frequencies go down, and then you see resonance at 1, 2, and 0, 1. And the positions of these are in fact in good agreement what you expect quantum mechanically, with some offset to the left and right due to the fact that we don't measure all the parameters perfectly. So it really makes sense that we see the quantized energy levels. And these energy levels are, of course, what you need if you're going to build qubits. And that's what people figured out how to do better and better over the 40 years that people have been working on this. Questions? I'm going over this a little bit fast here. Okay? So let me tell you what's really kind of interesting about this. We're used to the periodic table being our building blocks for looking at atoms, looking at molecules, maybe fundamental particles like electrons. You can make quantum system out of it. But here we can build a quantum system, not just from whatever is on the periodic table, but we can build now electrical circuits. with elements like capacitor, inductor, transmission lines, junctions, to make new artificial quantum systems. And of course, that's what we've been doing with qubits, trying to build a quantum computer and doing that. This has been done also for vibration systems, for coupling things to photonics, to light, nanomagnets. So in the 40 years, there have been a lot of people exploring these new artificial atoms, just showing that it works and then trying to make interesting devices out of that. So that's been a very exciting part of this field. Now, I want to talk about a couple experiments that we did that kind of illustrates what you can do with this new kind of artificial atom. And this was the experiment here that was done when I went to France, right after I did my thesis and worked with the Saclay group. And the experiment we did was to measure the time it takes when it's going under the barrier. Okay. Now, what's interesting is I did a podcast last week with, I think it's Star Talk podcast, where the professional physicist podcaster thought that this was instantaneous. Okay. And it's not. Okay. So, this is not something, everyone understands. And of course, using the uncertainty principle that I told you earlier, you don't expect, T to be zero. Okay. T tunneling. So what happened here? Well, what we would do, because we're making an artificial atom, what we can do is design it so the effective mass of this ball that we're throwing against the wall, okay, its mass can change over time, or it has a frequency dependence or time dependence. Normally, you can't do that with electrons or other things, but in this particular case, the electrical equivalent of mass can be changed while its device is cold and the like. So the way we do this is down here. We have this Josephson junction chip with an overlap junction about 10 microns in size by V4. And now we have a much more sophisticated microwave circuit. This is going to a two-dimensional coax, which is called a coplanar line. Up close, it's about 70 ohms. And then far away, we put a metal bar on top of it that's damping that goes down to 20 ohms. And what happens is we can take this metal bar and we attach it to a string to room temperature at the top of the cryostat, and we can pull that string and change that length and see what happens to the system as we change this length here. And since this is a transmission line, there's a delay going from here, reflecting off and coming back again, then that delay is what we can change with the string. So this is the plot. This is now the mean escape time, okay, instead of the escape rate, but that's just the inverse of it. And at 65 millikelvin, where you're at high temperature and you're seeing the thermal fluctuations, it's all driven by E to the minus delta over KT. And it was more or less flat. It oscillates a little bit as expected. It's more or less flat. Whereas when you go into the quantum tunneling regime, it then has a big change in escape rate here by about a factor of 4. Okay, so what's happening here? Well, what happens is when the load is right next to here, you have this 20 ohms right against the junction, and that's a lot of damping, and that's going to suppress the tunneling and give you a longer time. And then when it's far away, okay, then you're looking at a load that's 70 ohms, and it's not getting suppressed, so the time goes down. Okay, so that makes sense in terms of this, how the damping works, as I explained before. What's interesting is you get this continuous curve of lots of suppression and no suppression with the characteristic time of about 2 times 30 picoseconds. And that's basically showing you how long it takes for the system to tunnel out of it. What happens is it tries to tunnel, and the virtual tunneling event reflects off the end and comes back. And if it's long enough, then it tunnels before it has a chance to reflect back and interfere with itself. And that's why it starts to be flat. The data points are dots. The theory is the line. You see a very good correspondence between the two. And this is really great at this very early stage that we could do an experiment, measure everything properly, and have a really good test between the experiment theory and really know what's going on with the system. It gave us a lot of confidence that it was a clean experimental system. Okay. Yes.
So excuse the non-physics question, but it's an economist in the room. So the way I thought about your tunneling in this macroscopic world, right?
Yeah.
It's more than one electron. So can you have some kind of leakage, or is it always the whole artificial atoms that's?
It's more just think of it, I think of it as electromagnetic pulse, kind of classically. You have this phase oscillating that generates a voltage, and those voltage pulses are going down this electrical circuit and interacting with itself.
But it's always the entire atom that's escaping.
Yes, exactly. It's from the collective nature of all the electrons. That's what's interacting as a current or a voltage. You don't really think about the individual electrons.
In relation to what you said previously about the damping and it's losing the energy, you have to add more energy to accumulate for the losses. So do you essentially inject more energy as it's damping while it's tunneling?
So what happens is when it's up close and you get a lot of damping, then you have to have delta U be bigger in order for you to take into account the tunneling, and that's why it gets suppressed so much. So that's the basic physics. Now it's good, we have to go through the calculation and detail of quantum mechanics, but that's basically how it works. So the next experiment I want to talk about really deals with precision and control. And what we can do in these is we can actually make microwave photon states by making these transmission lines, this resonator of a centimeter, a few millimeters in length, it turns out. And we can generate very complex photon states. So what we do here is we have a qubit on the bottom here with the X and the loop connected to a resonance circuit to the right. And we can take the qubit frequency and detune it from the resonator so that they really don't interact at all. But then we can bring the qubit frequency up to be at the resonant frequency so that it can exchange light and exchange photons between the two. And what you have to do in this experiment is calibrate it very carefully by looking at the detuning and measure if the energy between the qubit and the resonator is oscillating back and forth over time. So this is on resonance when it's on. You can measure the oscillation that is coupling to it. You can then take it off resonance and turn that all off. So by calibrating the system, putting in the microwave pulses, you know how much light energy is going in, bringing it in and out of resonance. You can controllably move energy from the qubit to the resonator. And then what happens is you can build very complex states as shown on the right with this particular experiment. So in the left-hand column, it's 0 photons in the resonator and 5 photons in the resonator, okay? And this is something you can't generate classically, but with these qubits, you can do that. So you see 0 plus 5 has a 5-fold symmetry and a certain characteristic look. And if you look at the bottom, the experimental data, you can measure this particular picture of what the state looks like, and you can see that kind of pattern. And so for 0 plus 3 plus 6, you have another pattern, kind of 3 and 6-fold symmetric, and then you can generate those states here. So and to me, this is really nice because you can build this, build these experiments to put in whatever quantum state you want, a complex quantum state. But for me, in terms of building a quantum computer, what this indicated that we can put in microwave pulses and these control pulses, calibrate that in a simple experiment, and then generate something that's much more complex than that and get something that's quite reasonable and sensible. And it basically meant to me that you can do precise digital control calibration to get these quantum states and build them exactly how you want to build them. And that gave me a lot of confidence in might be able to build a quantum computer by doing that. So just to go on to what happened in 2019, when you do your PhD thesis, you're always tempted in your career to repeat it in a better way because that was such an enjoyable experience. So this is what happened with the quantum supremacy experiment. And here I'm recasting the question, does macroscopic quantum computation obey quantum mechanics? Can you do a complex quantum computation on a quantum computer and get it to work properly in the way that you expect? So this was the chip we built at Google, and I took my UCSB project over, and everyone worked really hard on it. It had 53 qubits. You can see more than 100 lines going around the outside to control this. It was in the 2D, about roughly a 7x7 grid, and to make that. And then in the quantum supremacy experiment, we basically did a quantum computation and showed that the result coming out of the quantum computer matched very well with what we were expecting, just doing a computer simulation of what it should work like. And the particular way that you do this computation with 53 qubits, there's 2 to the 53 states that you're computing on. It's called the Hilbert space. You can think of it as a computational space. 2 to the 53 is about 10 to the 16. So it's a macroscopic scale of a quantum computation. And it worked. Okay, it basically worked as you would expect. So that was very nice and important. So this is the experiment we did in 1985. Okay, this is what they did in 2019. It's about 35 years of technical advance. You can see it's more complicated, but we are able to get all that to work. Now I've been going very slow, and it's almost at the end of the hour. I'm going to go through next, and then maybe 10 minutes or so, give you a flare of what we're doing in the next, X years of my scientific career. And I think this is a really nice result, lots of technology improvement. But what I'm thinking of is if we want to make a useful quantum computer, let's say 1 million qubits instead of 53 qubits, it's going to take a fabrication effort that is going to be as dramatic as what happened from 85 to 2019. And we don't want to do that in 35 years. We're going to do that in 5 to 10 years. So, how exactly we're going to do that. So this is the problem when you look at these quantum computers that are getting made right now. This is a dilution refrigerator. It's about that in that diameter. You see lots and hundreds of wires coming down with various filters and components down here for the quantum computer. And that's that was for 50 qubits. What is a 1 million qubit machine going to look like? And you can see that just scaling up the wires can be kind of difficult. And what I would do is say this is very much like how computers were in the early 1960s, where you had individual transistors with a mess of wires connecting everything together to build the big computer. And of course, what happens going into the 60s to, let's say, the late 70s is people figured out how to make big integrated circuits and wiring up on the integrated circuits. And then you made something very compact and made something that could get better and better over the intervening 50 years, so that we now have very powerful computers. So we want to do something like that. And the basic idea, we think, is we can take all of this wiring and stuff here, and if we design it right, we can put that all on an integrated circuit. So 50 qubits would be something like this big, and if you make a big wafer of that, that could be 20,000 qubits. So that's what we're trying to do. Now, kind of from the business end of this, we're collaborating with a bunch of big semiconductor companies to do that. Here's a paper that we published last year on the archive where we kind of outline how we're going to do this. People can look at the archive if they want details. But down here in Colab, our company, what we're doing is we're collaborating with companies like Applied Materials who make the 300 millimeter tools that are used to do the fabrication. And we're collaborating with Synopsys, who does us the design software. And then at the high end, we're collaborating with Hewlett Packard Enterprises, who makes supercomputers, okay? And then 1QBit, for example, understands quantum error correction, Quantum Machines understands and builds control systems. So we're collaborating with a bunch of different companies to figure out how to make this happen. Let me talk about advanced semiconductor manufacturing. Let me just go on a little bit, since we're getting near the top of the hour. So one of the big solutions is to use Applied Materials. This is their maiden center. It's a several $billion clean room where they can make these devices. The real heart of it is using this called an Endura tool, which makes it on a 300 millimeter wafer with very sophisticated processing that they really understand what happens with the process as you build that. So normally this is a very expensive tool, too expensive for most projects to use. However, working with Applied Materials, they can retrofit the system relatively inexpensively and get it to work properly. Just to show you the basic idea that we have here is we have a qubit wafer that's at low temperatures, as they talked about this big, millimeter spacing, about 20,000 qubits. We then connect it to a wiring wafer, which takes 100,000 wires from down at 20 millikelvin and connects those wires to 3 Kelvin. If anyone knows about low temperature physics, silicon is considered to be a very good thermal conductor, kind of similar to copper. So you have to do something about that. And basically we provide thermal insulation between the two so that we can wire that and not having to have too much heat load. We then have on 3 Kelvin, we have quiet electronics wafer where we can put CMOS, other kind of electronics to control the qubit, and then have some copper alloy flex going to room temperature to do the readout and do more control. Then it gives us about 20,000 qubits, about something that's this big. And then we can connect these systems, pile them one against the other to make it bigger and bigger. So in one dilution refrigerator, about this big, we're talking about 100,000 qubits. Okay. So here's an artist's rendition of what this would be. You have a stack of dilution refrigerators where these are all connected together, and then wires going to a big rack of electronics that does the control and does all the classical processing that you need to happen to get this to work properly. So I would say one of the most interesting things about this is as we're going to the semiconductor industry and figuring out how to do the manufacturing, they know how to manufacture at scale, making a lot of chips and a lot of devices, and do that in a cost-effective way, because that's what you have to do to build, consumer electronics or even supercomputers. So you go through a list of all the things you need to do. fabrication, the qubit and carrier wafer is mass produced. Bump bonding and mounting, they do that already to make, the chips in your cell phone. CMOS control, yeah, that's mass produced. It's not large energy. People know how to do that well. Flex wiring, just PCB manufacturing. The dilution refrigerator is kind of the one custom and expensive part of this that we'll have to learn how to lower the cost, but I think that can be done. Assembly, testing, room temperature electronics looks like it. So since most of the system is electronics, and based on electronics, we already know how to make. We think we can, build this in a cost-effective manner. Still will be an expensive supercomputer, but we can do that. Okay, so summary, we've come a long way in 40 years. I'm frankly quite surprised at how well these systems work, given where we started from. But with all that progress, we think there's still some significant technical challenges and unresolved challenges in order to make a big machine. And that's what we're particularly working on. And we're going to leverage the semiconductor industry to do that. And we're doing this with a large consortium, large companies, startups, national labs, academia. And, we think we can scale to millions of qubits using this kind of technology. And that's what I'd like to do, our company would like to do in the next 5-10 years or so. Okay, so thank you very much for your attention.
Much, Martinis, for the very inspiring talk. We have time for questions. Any further questions?
That was a great talk. Thank you for the session. I have two questions. One is on a startup perspective and one is on the technical perspective. Being from, you have worked with academia for a long time, and also you have worked with industries. Why do you chose to work with a startup or founding a startup? Did it help in your journey? What is the important factor that you have an advantage when you are proceeding with a startup? One. And the second question is, I'm from a theoretical background, again, physics background, but not an experimentalist. So on the experimental perspective, when do you stop refining the process and you publish it? You told that when you were setting up the dilution refrigerator, it was chaotic in the beginning. And then you got into a point where it was getting better. So being an experimentalist, when do you start to understand that you are getting results, and when you do you stop refining it or you will continue the process?
Okay,
how?
I think I understand. So let me answer the first question. So in my career, I started out, I did a postdoc, but then I started out at NIST, which is a national metrology lab. And that's really good for me because in order to make the quantum computer and to characterize it properly, you have to understand metrology. So that was really useful for that. But then at some point, I wanted to really start thinking about building a quantum computer. And the metrology lab, they kind of want you to work by yourself or one other person. So the way that it was constructed in National Lab didn't work. So I went to the university and then, started really working on all the technology we needed to build it up. Then that was really great, very successful. But at some point I decided, we need to make hundreds or thousands of qubits. And it would be very hard to do it in a university. And the reason why, it's kind of interesting. In a university, you can start an institute for doing something like that. But there, people who work for you, scientists who work in that institute, are in what's called soft money. And for them to get promoted and do well in their career, they have to publish papers. But to make the practical, advances to it, you kind of have to sit in the lab and build the hardware and the like. So that kind of didn't match so well. And then at the time, we had the opportunity to then move to Google, which meant that people could be hired as permanent staff, focus on that, and do that well. And that led very quickly in what, 5 years, about 5-6 years to the quantum supremacy, where we had the 53-qubit device, and we were able to do a very sophisticated experiment there. So Google was nice, but then kind of at the end, Google kind of turned into this corporate dinosaur where they wanted to do their thing. And, like I was telling them, well, it's not going to work this way. We have to do it. And they just couldn't understand that, change the management, the like. So I decided that that wasn't so good for me. And then with a startup, you can do things exactly how you want to do. Okay, provided you have enough money to do it. So we're in that kind of uncertain stage. We're trying to raise the money. But all of these places were really interesting for my career and kind of made sense at the time. But, I really had to leave Google in order to come up, to have the vision to say, well, what is it we really want to build? Because everything that every superconducting qubit company is doing is, a vision I had, let's say in 2000 or so, and everyone's done it on their own. That's great. But I think that vision's not going to go anywhere. So it's kind of by having your own company, you're free to invent that. And then, at the same time, we have to collaborate with Applied Materials and, these things. And that's kind of beyond what you can do in academia, I decided. So, that's the way to do it. In terms of, let's say, I think that I'm going to interpret the second question as kind of technology development. And how do you know that works? So what happened is I tried to do every experiment so that when we finished the experiment, we didn't collapse over the finish line. Like we were still running hard. And that meant the next experiment we could do based on what we were doing before. So I spent a lot of time in my academic lab really understanding the basic technology, building our own electronics, building our own chips, understanding the physics really well so that we can build on it and then get this done. And that was a very conscious decision of me to develop the technology, even though it wasn't, let's say, giving you the Nature or Science paper that you want. If you're building technology, you're building up so that you can write those good experiments. So traditionally what I did is when the student came in, they started with a fab project or a little build project. And by the time they graduated with all this experience, they did the nice algorithm and got into Nature and Science. So that's kind of the way I tried to run the project. But when I went to Google, that all brought down because we couldn't hire students anymore. And it turned out that we were not doing some of the basic characterization and building because everyone were PhDs and they wanted to, do their big experiment. And things kind of broke down a little bit at that point.
So in relation to our current ecosystem in computers is binary, it's zeros and ones. In relation to entanglement, it's zeros and ones at the same time. And in relation to what's currently here, which is cryptography with quantum key distribution, where it's able to, in real time, equate binary system and actually crack it because zeros and ones at the same time with entanglement. In relation to what you mentioned with the 5 million qubits as to what you're projecting, how are you currently manipulating the calibration of the microwave pulses within the quantum states? So you create essentially a shield when it comes to quantum key distribution. Thank you.
I didn't understand the question. Water experiments are not very much related at all to quantum key distribution. We're trying to do quantum computation and not communication. Eventually, we need to do that and work on that, but that's something for the future.
There's a question
There's a
here.
question.
Yeah, so
Here first.
one thing you mentioned is that we are increasing the number of qubits, but with the increase of number of qubits comes the increase of density of qubits, right? And one of the questions I have is that since we have two qubits and we have two qubits, and in the system we manipulate them separately, but when we have them in real dense position, is manipulation of one qubit going to affect the other one?
So, of course, if you're doing a gate between the qubits, the operation on one will affect the other ones. However, when you put in the microwaves, you can get crosstalk where you're exciting this one, but because it's not designed right, you're exciting one. And this is actually a big problem. And we spent a long time trying to get rid of that problem. And that's actually one of the amazing things about the quantum supremacy experiment, that we were able to operate it so that the qubits, whatever we measured, they did and predicted it, that's how they work. Now, there's kind of a couple reasons why we did that. Is first of all, you design the electrical wires so that they're shielded from each other as much as you can. But there's still a little bit of crosstalk. But what you do is you operate the qubits at different frequency. So if you're driving this frequency and you're driving this a little bit too, since it's a different frequency, not much happens to it. So there's a bunch of games you play to try to, make sure everything is working properly in that way. And what we did is we used tunable qubits, which is very different than what everyone else did at the time, especially, so that you can tune it to get these frequency spacings exactly right to get rid of these kind of problems here. So it's a big system engineering problem to that, and that's a really serious issue you have to deal with. Now, in the end, you want to make better chips so that there's naturally no crosstalk from one line to the other. And we were able to do that to some degree better over time. But when I left, that was still kind of a problem that needed to be understood. And we're doing research on how that happens and how to get rid of it. That's something we still need to understand.
Good afternoon, Atimafa, former manager of admissions and recruitment at Khalifa University. So for administrators like us, who are not scientists, unfortunately, mathematicians or physicists or economists, what would you think would be the single most important takeaway about macroscopic quantum mechanics that universities should understand? And second, what would you foresee would be the new fields or applications in addition to new skills, academic backgrounds that universities should start developing in students, for the next generation of researchers in this field? Thank you.
So for the first part, it was just taking this very basic question from Leggett, do macroscopic variables obey quantum mechanics? And to me, that was like the most exciting things I could possibly do for my PhD thesis. But not very many other groups thought about doing it at the same time. There were a few who were trying it. They weren't doing the experiment very carefully. But looking back on it, why wasn't everyone doing this? And what I would say to young people, if someone comes up with a good scientific question that's really fundamental and interesting, yeah, you should just try to do it. I mean, it doesn't come along very often that happens. So I was very fortunate. I was kind of at the right place at the right time. On the other hand, we really jumped on this project and made sure that it works. In terms of looking forward, I mean, I want to build a quantum computer. Many other people do. I think there'll be lots of opportunities to use that in interesting ways. I'm an experimentalist. The theorists are focusing on that. But I see very, nice calculations that you can do that if we can actually get the hardware to work well. So my job is to make the hardware work really well, make it scalable, be able to build a quantum computer, and I will trust that all the theorists will be out there with lots of things. The thing that interests me the most is doing quantum chemistry and quantum materials, because there's a very natural mapping. There's a reason why it's hard to simulate that on the quantum computer. It's this large Hilbert space that we talk about. So there's a very natural mapping. And I think if you could do that, there would be a lot of nice scientific breakthroughs and opportunities there. So that's what I'm hoping it'll be used for, not just breaking the internet. I don't want to build a quantum computer to break the internet. Okay, people are working on it, so that won't happen. But I think there's a lot of benefit to society from doing, quantum simulations.
Thank you.
Very good. We have a question, Fernando.
My next question, thank you. Your digital potential that you were showing us of the cubic case, and so you concentrate on the cubic case with one single minimum, but you have generically several minimum. Can you adjust your parameters to study the transition from one minimum to another one and to another one?
In principle, you can go from one minimum to the other. And in fact, there were some experiments, I did them, other people did it, where if it's not tilted very strongly and you have like a high enough temperature that you can escape and then retrap. And there's this retrapping physics that you can see. And in that case, you don't get exactly a supercurrent, but the slow diffusion down the well gives you a small voltage. That you see. It still looks like the supercurrent branch, but there is a little bit of voltage to it. So those kind of things we're seeing. Mostly it's a classical effect, though. The parameter range to get into that.
Next, we have a question over there.
Yeah, thanks so much for the talk. I had a question. So from your perspective, what do you think are some of the quantum speedups or algorithms that would benefit from quantum speedups, such as protein folding or or ML? Like, I know there are already some quantum-centric algorithms like Shor's or Hilbert's, but what are some, in your opinion, specific speedups that are relevant to quantum that we can currently do on classical computers, but would really benefit from a quantum speedup?
So I'm not an expert on all the algorithms and all the things, because I'm focusing on the experiment. But yes, people are doing things like this. And what I would say is right now, they're more doing demonstration experiments. I'm going to say toy problems. They're problems that can be solved with conventional methods, but you want to show that you can also solve it with a quantum computer. And that's very useful. It's good people are doing that. And then the question is, well, if you make a more powerful quantum computer, can you now get to a regime where you can't solve it on a classical computer anymore? And there are claims of doing this, and then people show that, well, maybe you can calculate. So it's still a work in progress, but I think it's very good that people are attempting to solve these problems. But, in my view as experiment, we just have to make a better quantum computer, and then these things will happen. So, we have the resource requirements of these algorithms. We're down here with our quantum computers. This is getting better, resource requirements. And then, at some point this will meet and people will be able to do this. The other thing that's interesting is once this meets and you start doing something useful and in the business sense, making money, okay, then part of the profits, you may have to pay off your investors, that's in the business, okay? But part of the profits can be used to make better quantum computers. And that's why, your cell phones and computers are so good, is that people have been able to take part of the profits and reinvest it into making better transistors. So that, to me, is going to be a big inflection point, where then we can have a lot more resources put into making it better and then solve more problems. But it's hard to get to that point. But fortunately, there's funding and there's a lot of ideas out there. The field's very dynamic, so we're making good progress.
There's a question back there, Nada.
Okay, so I think most of the technological inventions are based on fundamental research at some point. In this case, what will be like the percentage of fundamental research in all what we are seeing now?
Yeah, I get very annoyed when every once in a while, someone proclaims that all the fundamental research is done and it's just engineering at this point for the quantum computer. And I just think that there's still things we have to do. But I'm guessing right now, it depends on what you're doing and what you're trying to do. But somewhere between 10% to 30% is fundamental research. And but it depends how you define that. You know, when I do, I'll tell you my view here. If you're trying to build an algorithm, you're integrating the Schrodinger equation. Okay, that's fundamental to develop the algorithm, but you kind of know what's going on. Okay, so that's hard. And is it fundamental and practical? I don't know. When I try to build better qubits by trying a new material or a new process, I have very little to go on other than to try things and see if it works. And, that's called applied research, but it's fundamental in the sense that I really don't know what's going to happen out of an experiment. Okay, you have to try it and see. So, what's fundamental and not is very blurry here, because you're trying to build something practical as well as doing that. And, of course, what you have to do is build these things in a way that you can predict it. The reason you can build this cheaply is that, they know if they make 1 billion transistors, what their yield is. Okay, we're nowhere near that for that. So we have to get better at being able to be predictable. Okay, and a lot of it has to do with this, the research is how to make these things more predictable and work every time. So it's just a different way of looking at things.
Thank you for a wonderful talk in terms of the retrospective over more than 40 years. And so I want to go to the next 15-year outlook, and you made a very persuasive argument by showing the few thousand transistors going to 1 billion transistor and wafer integration, and implied that something similar can happen by leveraging current existing semiconductor technology in the quantum computing world. But, and you alluded to this challenge earlier, the big challenge is that the semiconductor world grew. Moore's law existed only because it's a techno-economic law, and it required a growing industry that was then able to reinvest profits into future technology. So my key question is, when will be this point when there will be an economically viable quantum computing industry out there that then can future accelerate to the million qubit processors?
So I'll answer that, but I would say the advantage here is that CMOS funds have developed all the instrumentation that I think we basically need. We have to figure out how to use these tools in order to make our devices optimally. So we don't need money to build the new tools, to invest in figuring out how to build the new tools. Of course, we have to invest the money to figure out what the processes are and buy the tools or use the tools. So we're really leveraging quite heavily off the semiconductor industry. But like I said, I think the really big progress will happen once you start seeing applications. That could be from 5 years to 10 years. It's hard to know, but it's for the first time in my career, I can kind of see that maybe happening in the foreseeable future. And that's kind of what makes it more exciting. But then, once that happens, then we can start doing it very well. So that's the big inflection point. Yes.
Question over there. Thank you for a great talk. And my question is a bit similar to the previous one. So I'm from like a machine learning background. So when the Google Velo came out, all AI guys become very excited, but there's still a gap. So I would like to know, if you predicted how many years can be for our AI guys can really use it, and is it time to look into the combination of AI as well, AI with that?
But people ask all the time to predict, and people have been doing that for decades now. Again, I would say 5 to 10 years. it might take longer. It depends on the details and on but a lot of fundamental and engineering details we have to get right. But what I would say is for the people who are thinking about, cryptography and quantum space, safe cryptography, they should be worrying about transferring it over, soon, because there's a possibility this will come, quite rapidly.
Thank you.
But I think it's hard to predict. I mean, I'm trying to do it as fast as I can, and we're trying to do a 5 to 10 year time frame to get that to happen.
Thank you. Do you think it's the right time for now to look into AI plus quantum computing?
Yeah, so I used to work for the quantum AI group at Google. And of course, Google is, very strongly thinking about AI. So this was a natural thing to do. It looks like there's a good combination between quantum and AI okay, so this is the use case in our Quantum Scaling Alliance has written about this, where you will use a quantum computer to solve, finding problems, quantum molecular problems, but use that as synthetic data to go into a classical AI, which can then be used to predict, what other molecules do. Because the problem is you need more data in AI to kind of predict that. And it's expensive to get that data by synthesizing molecules. So if you can do that with a quantum computer or parts of that, you can then maybe use that as a powerful way to predict it through AI. So I think this is the kind of way that it's going to use. I'm not saying that's the best way or whatever, but I think in combination, you can kind of see how that being powerful.
Thank you. It's a question. Thank you. Thank you very much. Thank you very much for your beautiful talk. It's a pleasure. I am former chair of mathematics at Khalifa University. So for 6 years, I debated the problem of what should we teach our students in math so that they would go into quantum computing, quantum world, and things like that. And I can see that you really think in a way that is very, very much an actual background of knowing what's a Hilbert space, what's the right behind it, and yet you're working a very practical thing. How can we tell people that think that just AI is enough to study these things, that you should go and really learn the basics and how much the basics really help you?
So if you're teaching math students about quantum, then in some sense it's simpler because it's matrix vector analysis and things like that. And one can kind of teach that axiomatically and understand how the algorithms will work. So I'm not an expert on this, but I think one is able to do this, and there are textbooks out there. If you want to teach them about more experimental techniques, then that's a much more difficult problem. And so what happens is I'll just tell you for our company, we're hiring. So we have to hire PhDs who really understand how the quantum works and to use our devices. But we do hire computer scientists and engineers who know about fab, who knows about software, other things. And what they've traditionally done is taken a master's course, say at University of Wisconsin, other places do that. So it's kind of in 1 or 1.5 years, they learn enough quantum to be useful for a company. So that actually works pretty well. And then, they come for us, they know enough engineering background to help us, and then we slowly build up their knowledge on quantum. So that's kind of what we're practically doing, because we do need a workforce that's not just physicists, computer scientists, mathematicians, engineers, microwave engineers, fab engineers. it takes a lot of different skills to do this.
Thank you very much.
Hello. Just I am professor of Sharjah University. I'm the field of quantum physics. I'm a quantum computing person. My question is the following. You have presented the fact that the wire, because in the quantum computer of IBM or Google, you put it, all the system in refrigeration. Now, I think you presented something, but if I'm not misunderstood this, I didn't. I think, is it realized the fact that the qubit on the wire is not refrigerated? That means you can decompose the computer in different components without obligation to put all of them in one refrigerator. Is it realized, this idea? I think you
So
is it a future idea?
So what happened in the quantum supremacy experiment
Yeah.
is that we calibrated single qubit gates and 2 qubit gates from all the different things or whatever, and just calibrated that. And then we ran a complicated general purpose calculation and got the right answer. And when you checked, what was the errors in getting the right answer, that was completely consistent with what the errors were that we knew for the single and 2 qubit operations. Does that answer your
No,
question?
maybe you misunderstand my question, or maybe I didn't formulate it the right way. I'm speaking about the global, the quantum computer. Usually you put it in refrigeration, you reduce the temperature as maximum. So usually you put all the computer together, that is block together on Google GPM. Now you have presented, I think, one scheme. There is possibility to have some qubits linked with a wire that is not refrigerated. That means you can decompose the computer in different parts without an obligation to put it to refrigerate all of them. Is it this idea realized or?
Yeah, okay. So first of all, the control system and the decoding system is going to be complicated enough. You want that at room temperature, so you have to separate out. However, the qubits that are cold, we're going to build 20,000 qubits, but we can connect it to a wafer next door through simple capacitive coupling, and also you can connect it through microwave coupling over longer distances. So there's 2 ways to build a really big system. Is to have many dilution refrigerators and they share vacuum and the like, which is kind of not modular enough. In order to connect them, people are talking about connecting them with optic system, which you just plug in. However, the transducers between microwaves and optical frequencies are not quite good enough yet. People are working on that, and when that gets to work, that's the way to do it. I think there's a way to connect refrigerators, even though they're separate. It's a complicated way, but there might be some ways just to connect it with microwaves.
Because we have a patent about how to connect the qubits together without refrigerating the wire. It's since lifetime.
Yeah, if you use optics, you can do that, but as soon as you go to microwaves, you're always gonna. It's hard to do that without a superconductor and make it work right. Yeah. So you really want to cool it, and that's kind of a negative of the superconducting case right now. But people are working on the optical connections, and if we can get that, then that would be a great way to put it together.
Good, perhaps last question.
So we've got 2 online questions. The first is the wafers, the printing of qubit on wafers. Isn't there a wave edge issue in qubit application? When printing qubit on wafers, significant performance degradation occurs from the center towards the edge. That's the first question.
So I didn't quite. Can someone repeat? I had very bad hearing and I didn't quite understand.
Okay, let me read it out again. So the question was about printing of the qubits on wafers. You can read it. Just printing of qubits on wafers. isn't there a wafer edge issue in qubit fabrication? When printing qubits on wafers, significant performance degradation occurs.
Yes, from the center to the edge. Yes, so that would happen when you do the qubit wafer. That's actually doesn't go to the edge of a big cube of a big wafer. So you actually only would take, 14 centimeters across out of a 30 centimeter wafer. So yes, but you do have to worry about, center to edge. And the nice thing is the people in the CMOS industry really work hard on making sure that they can yield wafers. So this is something that the companies like Applied Materials, have thought about and know how to do pretty well. But yeah, that's something we have to worry about.
Thank you. And then the other question is about photonic approach in terms of scalability. It seems to have a lower entry point from a production point, and can also be scaled easier on lower infrastructure and naturally integrates with network infrastructure.
Yeah. So it's very difficult to compare all the different qubit modalities and to really know, which one might win. Okay. And that's why I think it's good that they're all being funded and we're just going to see what's happening. Now, with the optical case, they make a case where they can scale up by just connecting fiber optics and that they're fast and that's great. So there's a lot of nice things about the optical system. But the one thing that is not talked about much, that's very important, is the fidelity of the operations, the errors of the operations. And for example, my understanding is if you take the cyclonic approach, that they need to have something like 99 point something% the detection of the optics, which is really, really hard to do. My old friend at NIST, measured that, and that's a, huge metrology experiment that's really difficult to do. And I'd say for the optics, we don't get that much information on how good the component quality is that can make you do that, make you understand what's going on. So, we'll wait and see what happens and whether they can build it. They certainly have enough funding to build some interesting systems. They're making a lot of progress, but it's component quality that matters. And the nice thing about superconducting qubits is that we measure the qubit quality, to good gate fidelity. We build, 50, 100 qubit systems. We know how it works collectively. So we have a lot of benchmarking data knowing how that works. Okay. And then of course we have the scaling problem that we have to deal with. So the big thing that I would maybe leave you with is the problem when people talk about their qubits, they also always talk about what's good about their qubits. But in reality, you have a bunch of things you have to do right. And it's usually the thing that's the worst performing that you need to fix. And people tend not to talk about that, for, obvious reasons. My talk is all about fixing the worst thing, which is the scaling. And, I focus on that. And I try to be different and try to be honest about, what is the big problem we have to fix.